Hello, my name is Roy. I'm a computational engineer at CrossCompute. In preparation for New York City Open Data Week, I'm going to show you how to fit a spatial regression model and prepare a dataset that you can use to fit a spatial regression model. Let's start by going to bit.ly/crosscompute examples. This is a table of different examples of tools that have been created on the CrossCompute platform. If you scroll down, you'll see one that says compare spatial regression models on Airbnb listings and prepare spatial regression dataset. If you click on the tool link, you can see what the tool looks like, and you can run it. And what this tool does is it loads these Airbnb listings for Vancouver. If you pick some features that you would like to include in Model 1 and features that you would like to include in Model 2, it computes the mean squared error for different types of models. So this OLS stands for ordinary least squared, LAG stands for the spatial lag model, and this is for Model 1, and these are for Model 2. And it also shows the coefficients that indicate the potential influence that that particular feature is having on the model. For here, the definition of mean squared error is just a way to compare the performance of each model, and of course less error is better. So for here, of all the models, it seems like ordinary least squared mean squared error without spatial lag performed the best using these particular features. So we're going to show you how this tool works. If you scroll up and you click on the tool notebook, you can see the code that was used to generate the tool. Let's start a numerical, tiny, I'd say an hour session, and click run. So it's starting a Jupyter Notebook. Okay, so this is the tool. And this is the code that the tool runs when you click run. Before we go into the details, I just want to emphasize 3 buttons that are specific to CrossCompute. So the white button is to back up your notebook while you're working on it, the blue is to preview the tool, and red is to deploy your tool on the site. So if you click on preview, you'll see the same demo that you saw before, but only in a kind of test development mode. And the development mode is a little different because it also shows the raw standard output. Okay, so let's go back into the actual code. So how does this tool work? Spatial regression is same as any other kind of regression model, and regression just means when you try to predict the value of a numerical variable using other variables. In this case, we're trying to predict the price of an Airbnb listing by paying attention to certain factors. And here you can select which factors you want to pay attention to for each model. Okay, so if this is your first time using Jupyter Notebook, you select the first cell and press Shift Enter, and you can run through the different stages. So here we collect the features that were selected. So you can see it identified the features. We import some modules. This is how you would install a module if it doesn't already exist in the environment, but we don't have to install anything custom for this example. So it's downloading the listings, it unpacks the archive, it loads the table using pandas read CSV, and we're looking at the first element. Here we're just showing the different data types of each column, and here, thanks to Stack Overflow, showed us how we can just isolate the columns that have numerical values. This code is based on an example provided by the link that's at the top. Okay, so now we limit the table to just the features that we want to include in our model, including the target variable price as well as these dependent variables. So this is the independent variable, this is the dependent variables. We normalize and we rescale the price according to logarithmic scale. We prepare some spatial weights. You can look up more about spatial weights. This is documented in the PySal package. Okay, so now we use ordinary least squares. It presents some statistics, including your p-value. And if you remember, p-value is a probability of this result happening if things were random. So okay, so the things to pay attention to here are, we're just going to pay attention to the coefficient, where a larger coefficient indicates that this probably has a larger influence on the price in this model. Here we So here we fit a different kind of model. Instead of ordinary least squared, we'll fit the generalized spatial lag model, and we evaluate the same kind of portions. And you can use betas to access the coefficients that are in the same order as the features that you put into the model. And finally, to compare each model, we'll use the mean squared error metric, which just computes the average squared error of each predicted value with the actual value. So that means it computes the error of each row of the predicted value predicted from the model, as well as the actual price versus the actual price of the listing. So here is just, we combine those fits and we generate our result, and this was the result that you saw on the tool. Okay. So this was the example of the tool that you saw, and specific to CrossCompute, you can, if you print a standard output, a certain data type such as text or table or geotable, you can have it output as a result of the tool. Okay, so now we have a basic idea of how to fit a spatial regression model if you want to test for spatial correlations. Just to review, you need to identify your you need to prepare your data set in a format that looks like where you have one column, the dependent variable in one column, the independent variable that you want to predict in one column, and the dependent variables in all the other columns. So this is the format that we want to prepare our data sets in order to run spatial regression or any type of regression model. Okay, so now the next step is we're going to prepare the spatial regression data set. Let's click on the table, the file directory. Click on Prepare Spatial Regression Dataset. So now let's cover how to prepare a dataset that you can use for regression. First step is to identify your independent variable, the variable that you want to predict. Then identify your dependent variables. And we're going to use 3 datasets from New York City Open Data. We use a facility database, which is a table of different buildings owned and operated by the city. We'll use the disease surveillance data. So this is the facilities database. This is the disease surveillance data, which just is a table of different neighborhoods and the frequency of incident rate of different diseases, as well as the air pollution raster, which is a image of air pollution measured for different types of along different metrics such as nitrogen dioxide, particulate matter, and so on. Okay, so we'll cover preparing a dependent variable by aggregating over a column, preparing neighborhood polygons, preparing a dependent variable by aggregating over an image, and preparing a dependent variable by aggregating nearby coordinates. So 1, 3, and 4 are going to result in a new dependent variable column. So let's start. So first let's press Shift Enter and define these convenience functions for downloading from a URL. Okay, so let's prepare a dependent variable by aggregating over a column. We're going to average the age-adjusted rate per 1,000 population over each neighborhood. So let's download the data set. We're going to load it. This is what it looks like. So we have our neighborhood, we have the disease, we have a number of cases, we have the incidence rate per 100,000 people, and age-adjusted incidence rate. So what we want to do is get the average age-adjusted rate of all diseases aggregated over the neighborhood. So we have 43 unique neighborhoods, and we're going to use group by, get the average, and so we have aggregated by each neighborhood the age-adjusted rate per 100,000 people. So here we use group by and mean. Okay, so now what's missing from this table is for each neighborhood we also want the actual spatial polygon of the neighborhood. If you look at the data dictionary for the file that explains how the dataset was created and which of each of the columns mean, it says that each neighborhood actually corresponds to a set of zip codes. So what we're going to do is we're going to also get from the census the polygon corresponding to each zip code, and let's make this a little smaller. So we're going to get the polygon corresponding to the zip code, and then get the spatial union of all of the zip code polygons so that we can get the neighborhood polygon. Okay, so these are the zip codes by the neighborhood code. Now we download from the census. So this is the census data. Let's take a look here. From 2017 that shows the polygons for each zip code across the whole US. Okay, let's load it. It looks something like it's quite a big file. So here's the zip code. Here's the polygon. Okay, so we have so now let's just do a little exploration of the zip codes that we have in New York City. Okay, so let's draw from the US Census zip code table all of those zip codes that are in our New York City neighborhoods data set. So when we draw it, it looks something like this. You can get for a specific zip code 10282, which is a zip code for Stuyvesant. Okay, so now what we do is let's use the unary union function to get the spatial union of all the zip code polygons for each neighborhood. So that results in a dictionary like this. And finally, we're going to create a new column in our aggregated disease table called geometry object that simply assigns for each neighborhood the geometry that we computed earlier. So now we've just added to the table we created before, the aggregated table, we've added a geometry object. So this is the neighborhood polygon for 101 Kingsbridge, Riverdale. And we can also get our favorite Fordham Road right here. So this is the Fordham neighborhood in the Bronx, which is the headquarters for Yamule. Okay, so now finally let's go over, well actually second to last, now let's work with the New York City air pollution data set. So the air pollution data set is an image so it's a set of images that where each pixel indicates the annual average predicted surface for each of these measures of pollution. And we're going to focus on nitrogen dioxide, which is particularly toxic. Okay, so see what's going on. Okay, we just need to get a zip file. One second. Okay. You won't see this problem. Okay, so what we just did, we downloaded the zip file. Let's show so these are the images for nitrogen dioxide. We're going to pick AA2, which I believe could correspond to a year, or I'm not really sure, but it's one stage of when they collected the data. We're going to install the raster IO package. Didn't work. Let's try again. Okay. If you ever get a -9 error here, what you can do is, there's probably a memory issue, so you can just restart the kernel and run it again until you get a 0. Okay, so let's load the image. Let's get the coordinate reference of the image, which we'll use later. So the coordinate reference defines how each pixel corresponds to a specific location on the Earth. Okay, we're going to load the image array. Since we're using a New York spatial reference, these are the x and y coordinates for this particular pixel. This is so the actual image is 155 pixels high and 157 pixels wide, and the largest value is about 46. The smallest value is this epsilon value. So you have to know that this is probably indicates some null value. Okay. So now what we did is we reduced it to a 2D array, and let's just see what it looks like. So you see, of course, there's a lot of pollution right in the center of Manhattan, which is where we are right now. Okay, so now let's use the spatial projection that we had before and convert. Let's define a function that takes longitude and latitude and converts it into the same spatial reference as our air pollution raster. So we take our source projection, longitude and latitude, and our target projection that we had before. Okay, let's install Fiona. Oh, I'll get that again. Just a memory error. Let's try again. Restart. Run all above. If you do get this consistently and you're using a large data set, I recommend starting perhaps a medium-sized instance next time. Okay, we're still getting it. Let's try closing some things that are running. Don't need that. We don't need that. Okay. Let's also shut that down. Okay, let's run this again. And what we're going to do now is we're going to use each neighborhood polygon that we got previously, and we're going to sum for each neighborhood the air pollutants of nitrogen dioxide that is in that neighborhood. Let's wait until this is finished. Let's see what it's hung up on. It seemed to have started. Let's try again. Restart. Okay, here we are. And the way this works is that we mask the raster data by our polygon, and we have to make sure that our polygon is in the same spatial reference as the image. We also remove set all. When you compute the sum, if you get something like negative infinity, it's because you have some strain, like super small negative values in the image array. So what we want to do is we'll set those super small values to 0 because there's no negative values in this data set. So you can see that the sum nitrogen dioxide particulate matter for the measured as over this this particular neighborhood is 2,248. And we'll do the same thing over all of the neighborhoods. And now we've just added a column called pollutant sum. In particular, we dropped the rows that do not have a geometry by using drop NA over subset. Okay, finally, let's cover how to prepare a dependent variable by aggregating nearby coordinates. So we're going to use KD tree, and we're going to use a version of KD tree that operates on longitude and latitude using arc distance. Okay, so this is the facilities data set, which is all the buildings that are owned and operated by New York City. Okay, this is owned and operated by the Departments of Parks and Recreation. So we're trying to identify, extract just the table of recreation centers. So we're using string contains recreation as an approximate way, and here are the first 3 columns. So there's 94 recreation centers, or areas that have recreation in the name. Let's also extract the table of schools. So now what we want to do is that for each recreation center we want to count the number of schools within a half-mile radius. So to do that, we're going to use a KD tree. First, we'll put the longitude, so longitude is first and latitude is second. So for each row of the school table, for each school, let's create a row that's the longitude and latitude of that school. Then let's create a KD tree using those school XYs, using the arc distance metric because we're using longitude and latitude, and where we're defining distance using miles. You can also define it using kilometers. But we won't go into that. Okay, so here we actually do a query of schools that are half a mile away from this particular location. And we want to get, we can specify how many we get back, and we just want to get all of the schools in ranked order that are within half a mile of that location. And what happens is then you get an array that is school count long, where school count is 6,000 schools. But a lot of them are not a number, which means they're not actually valid. So to do that, we'll filter by the ones that are valid, and we end up with 31 schools that are within half a mile of this location. And finally, let's add that as a value to our table. So we consolidated what we just did before into this function called getSchoolCount. We use the pandas apply function for the data frame along each row. And we end up with a new recreation center table that has a column called nearby school count. So for this particular recreation center called Wheel North Site Redevelopment, which does not sound like a recreation center, but there are 8 schools within a half-mile radius. So we've just shown you how to prepare a data set that you can use for regression, and particularly spatial regression, by combining different spatial sources. Thanks, and we'll see you Friday.